think today we'll do mostly some review before moving to the new topic. Okay. So do you feel like I'm going too fast or too slow, or any comments in general so far?
Looks fine. Depends on the class.
Depends on the class? Okay. So let's make a few comments about the very important point, which is universality. So let's emphasize that we already have seen quite a bit of universality in this class. So first, we saw it with random walks. So with random walks, we saw that if I start with some random probability distribution R, right? So we start with some probability R, which is parameterized by some cumulants. Right? What are these cumulants? They are these averages C1, C2, C3, and so on, defined as the average of exponential of I k of R. So it is just a generating function once I expand in R of average of R squared, and so on. And if I write this, if I take the log of this average, I define this is my definition of my cumulants, as a sum of some C n I k to the n, where n is bigger or equal than 1. So we start with some distribution. So these guys parameterize the distribution. So we think of these guys as couplings. These are like my microscopic couplings. I start with some random log, right? So let's assume this one was the bias. So let's start with this one being 0, but otherwise this would be, if we want, no bias. And then we saw that as we zoom out under RG, we flow to a distribution where C2 is non-zero, but all other Cn are equal to 0. Right? In other words, this average is a Gaussian because it only has quadratic term. Right? So this average is exponential of quadratic term, which is a Gaussian. And Fourier of Gaussian is Gaussian again. So the distribution which has this property is a Gaussian. So probability of R is e to the minus some constant R squared after a few steps. And that's the idea of universality. Doesn't matter, all these couplings here, they are irrelevant. Okay, so I would just like to make a few comments about now how do we see the same universality in the Gaussian model, because we have seen by now several times that the Gaussian model and the random walk are basically the same thing. And let's illustrate a little bit of universality by recalling what we did. We computed the propagator, g of r, which was the expectation value of two spins. And let's remember very carefully what we saw. We saw that on the lattice, it was given by 1 over the number of sides, sum over the momentum in the Brillouin zone, e to the I k dot r. I'm alternating between capital R and big R. Capital 1 over k squared r squared. And then we add here, say, u plus 2t sum, depending on how many dimensions you are, cosine of k mu. This was the inverse in Fourier of the matrix A. Then we said that this is approximately equal to the integral ddk over 2 pi to the d e to the I K dot R over the same thing, U plus 2T sum over mu of cosine K mu. And then we said this is approximately equal to some let's write it. Integral d dk 2 pi to the d. If I expand the cosine, what do I get? I get u plus 2td plus t k square e to the I k dot r. And then we said this was approximately equal to e to the minus m absolute value of r. Okay, so now let's recap what were the approximations. So let me ask you, so this was exact, so here there's no approximation. When is this true? What is the approximation going from here to here?
That the gradient sum has a lot of points.
Which is the statement physically it means?
R is very big.
No. No, that's very not true.
The volume of the lattice.
Yes. So when the volume of the lattice is very big, the momenta are effectively continuous. So this is true for a large lattice. But the spacing R can still be 1 or 2 or 3. Just it's an infinite lattice now. We have a very large lattice. But the spacing is still very much discrete. And the cosine is still here. So when is the second approximation valid?
No, it's larger.
Now this is for R much bigger than 1. 1 is our lattice spacing. We don't carry it around, but if we did, it would appear here. Right? Because then we only care about small momenta. Notice that here, the momenta, K, right, is in the Brillouin zone, so it's between pi. Whereas there we expanded small momenta, but then in practice, after we expand out, these take values over all possible momenta, right? Good. And what did I do to go from here to here? And when is this approximation true?
Look for the nearest singularity in the.
Yeah, but physically, what's the approximation going from here to here? That's mathematically what I do to compute it, but physically, I already took large lattice, I already took radius much larger than 1. What do I do to go from here to here?
The R times m is much bigger.
Exactly, so now it's R, it's even much bigger than 1, is much bigger than 1 over the mass, which is defined as psi, the correlation length. This can be hundreds of sides in correlation. The correlation length. Whereas what is this correlation length? You see that normally what's convenient is I remove this t from here, then I put it here over t, right? And there's just an overall t here, right? Did I put it in the right place? Probably not. 1 over t. Then this is a constant, who cares? And this is m squared. Right? So this is the effective correlation length. But you see, you could tune, by tuning this t and this u, you could try to make it very small. Right? So large mass means small correlation length, and very small mass means longer correlation length. Okay. Now, let's suppose that we were we are considering our Lagrangian, which is 1/2 S at position R, matrix A R prime, S at position R prime, and this A was U times, if they are at the same position, so let's write it like this, delta of R minus R prime equals 0. So we put like this, right? The distance is 0. I don't know. Should we put comma 0? Let's put comma 0. Plus, I don't remember if it was plus or minus, I don't remember. T times a delta function that says that the separation R minus R prime is 1. Okay? Are you with me so far? And this graph, this guy, we could draw like this. We could say that I have my lattice. And this is an interaction with these four neighbors. Right? From the point of view of this side here. And we could consider adding an interaction of next to nearest neighbors, say these guys. Okay, so how would we do it? Let's do it right here. So we would say plus, if we add this guy, T prime delta when the separation R minus R prime is 2. We could also add, so I have another color, so I can add that, an extra one here and here. How would we add this? If it's the diagonal like this? Plus another coupling, T prime prime, and then how would we write this one without diagonal? What's this distance?
Square root.
Yeah, delta R minus R prime square root. And so on. We could have more terms like this, but let's suppose we add these three. Now this is an example that you see. From our point of view, we were expanding this down, right? We were treating, last time, when we were mapping to random walks, we were treating this as saying, this induces a step. It allows me to jump by a step. By the way, is it too hot here? It's a little bit hot, right? Let's turn on the AC. So this T was a step, right? This is, in the random walk picture, we were jumping to the neighbors. Now, if we redo the derivation with last time, with this T prime, now I can jump 2 units. And with this T prime prime, I can jump diagonally. So this is changing the microscopic details of my jumps, right? So in the picture, if I map to random walks, what will change? What will change is that now the microscopic rules, the probability distribution at the microscopic level is going to change a little bit because I can jump to neighbors, to next to nearest neighbors, and diagonal. So I changed a little bit my starting probability distribution. Instead of being just for neighbors, now I have more probability, more possibilities. What will happen for large distances? All these details will be washed out, and I will go again to the Gaussian. So we expect that all this should not have that much of an effect. It should all be encoded in some simple effective parameter at strong coupling, at large distances. So how does it work? So let's suppose we have these terms. How does it change these formulas here? Well, this term here, let's call this this term here our cosine term. The only thing these guys will do is to change this cosine term, right? This cosine term now would become what? Well, it would become the same. And tell me what I should add. Plus what? By adding these terms, how does it modify that cosine term? By adding this yellow and this blue term. So?
Cosine of 2k?
Yeah, is it clear for everyone or not? It's not clear? Because what is that? That's the Fourier transform of this, right? So it's just Fourier transform. Fourier transform of u of delta function is 1. Fourier transform of this is just e to the ik, e to the minus ik, right? So is it clear or not? So this, the next term is 2 t prime sum of cosine of 2 k mu. Is it clear or not? Please. What's the other term due to the rule?
Square.
So wait. So what is it? For example, for the rule.
With the square root.
So you want to put a square root of 2 here?
Yeah.
So this is obvious. Okay, the way I wrote it, you might actually. Yeah, that's not true. That's not true. So let's be a bit more careful. Not more careful, but let me help you a bit. This means that delta of r is equal to r prime plus 2 e hat mu, right? Summing over mu and over plus minus. That's what this term is, right? Okay, so I gave you a hint for the yellow term. With this hint, what do you think? Or let me give you another hint. Here there are 4 terms. 1, 2, 3, 4. And blue, in yellow there are 4 terms. 1, 2, 3, 4. There are 4 terms in yellow. Where are the 4 terms here? I sum over 2 mu's, say, if it's 2 dimensions. So this is 2 terms. Where are the 4 terms?
Well, originally I had a sum of exponential.
Exactly. So there are these 4 exponentials, right? So each exponential is 1 yellow term. Good. I gave you more than enough hints. So now tell me what's the blue one.
Oh, now I have 8 terms because I have to do E1 plus E2. To diagonal direction.
Why 8 terms? There are 4 dots. So it's still 4 terms, but what are these? What would be this interaction here?
It's E1 plus E2.
Right, exactly. So this would be an interaction of E1 plus E2 direction. Good. So what type of exponential would it generate?
Oh, we will generate a cosine without a factor.
What does it mean? Cosine, what cosine is it? What factor is it? Just this one.
So it would be E to the K dot E1 plus E2.
Good. That's indeed true with an I, which is e to the I kx plus I ky. Right? So it's not square root of 2 times 1 component, it's 2 components that appear here. So here we get 2 t prime prime times cosine of kx plus ky plus, if there are more dimensions, there would be kx plus kz, right? Depending on how many dimensions we are. If we're in 2 dimensions, it's x and y. Otherwise, it would also be x and z. And we also have this, for example, this cosine describes these 2 possibilities. These guys would be the minus sign. So we would sum in this case over plus minus. Okay, good. So indeed, so if I want an exact expression, That's what I should plug here. So this is what I should plug here. This is my cosine term. And now it gets modified. Now, does it mean that here the results are different? For my propagator in this expression, will I get different results for this expression here? By changing this cosine term?
I'm sorry, what was the plus minus? Why are we something over plus minus?
Well, I have E1 plus E2 and E1 minus E2. So this gives Kx plus minus Ky. Right? So there is one with exponentials like this and one with a minus sign here. Okay, good. So this is the new cosine term. So I'm asking you, if I plug it here, I get the new cosine term, right? So this goes to the new cosine term. Does it change the result of this integral? Changing this cosine term to this new cosine term. So I change this cosine term by the new cosine term there. Does it change the value of this integral? This one, have this one. Not that one. I'm asking about this one.
The large lattice.
Yeah, the large lattice, this expression. Does it change? It changes. Because we have a very large lattice, but if the distances are small, we see these microscopic things. Right? So this expression here for large lattice, it means it's a very large lattice. I don't see the boundary, it's huge. But I do see the lattice points. Of course it matters. Right? So here, it matters. Because we are not studying field theory at this point. We are studying just a big lattice, but seeing the lattice spacing. Our spacing is 1, and we see the chunks. Right? We see that here, to linear order in these perturbations, next to linear neighbors start talking to each other. Before, it was only next to linear order, because they had to do it in 2 steps now. Right away, they talk to each other. So, of course, it changes. But then, what happens when we go much bigger than lattice spacing? When we go much bigger than lattice spacing, all this cosine term does is the following. This cosine term, you see, it's even in k. For each k, there is a minus k, the way we wrote it, right? This is the notion, this is the analog in the random walk of not having a bias. We are not saying that one direction is better than the other in the random walk picture. And because it's even, this is because this expression is even, right? This is equal to some constant times m squared plus k squared plus order k to the 4th at small k. Right? This constant is the analog of that t minus 1 that's alone there. Here I factor it out. Because what matters is the relative strength between k squared and m squared. So this m squared, let's put a star to indicate it's not the same m squared. Right? So all that this would do in this picture, as, what's your name? Sorry, I forgot. Sorry? Rolando. As Rolando pointed out, all this does here is change this mass to some effective mass. And that's this notion of universality. Various microscopic probabilities of random walk give different Gaussians with different parameters, but that's the only parameter in the Gaussian is basically sigma. It is what is the average deviation. So all that does is a star. And otherwise, that's all we care about the lattice in this case. All these higher things would be washed out. So we would say that these things here, this order k to the 4, and you see that they are exactly the analog of this higher case in the cumulant expansions. All these guys, we say they are irrelevant. And they are irrelevant in the same sense as the irrelevancy in the random walk. They are irrelevant in the sense that they don't show up at large distances. Okay. Now let's try to see this. So we see this very explicitly, right? I mean, we see that these extra details of the lattice at large distances don't matter. It's the same thing as in the random walk. The small details get washed out, and they are all encoded in some finite number of parameters, right? And let's see how this will manifest itself in a more field theoretical language. Right? So this was, we had a lattice, we had a precise lattice description, and then we computed everything explicitly and saw that at large distances, all these next to nearest neighbor interactions do is renormalize a little bit our parameters, and the net effect is the same. So how would we describe this in a more field theory language? We would say that this Lagrangian is roughly, well, there are these integrations here, so it's roughly an integral over d-dimensional space. This is when we are taking a field theory limit. Right? And then this Laplacian derivative was something like ds, right? Mu. If I integrate by parts, this is nothing but s Laplacian s minus, where this is the discrete Laplacian, the continuous Laplacian, which is the continuous version of the Laplacian that we were seeing before, right? That couple of nearest neighbors. Plus a constant m squared times s squared. Okay? And this s is a function now of r, continuous perimeter r, which is much bigger than the lattice spacing. And yeah, that's it. Right? But when we went to this field theory, we approximated these discrete terms here, right? We said the following. You see that all these discrete terms, right? All these terms they are some kind of averages of s around the midpoint. Right? I take these 4 points and I average them, right? So this way of averaging, I can add and subtract also the value at the origin. That's the definition of Laplacian. Right? What's the second derivative? This value here, minus twice the value at the origin. Right? So those are the definitions of discrete Laplacian. So all these terms, to leading order, they approximate to the Laplacian plus a constant, right? So if I just subtract the value at the origin, these guys, they all go to this plus corrections. These corrections are these corrections here, of course. Right? So that's what these corrections are. So let's work them out a little bit in field theory language. Let's write what they would be. So do you want to guess? How would I write those terms, those extra terms that say that, well, this average is not exactly just the Laplacian. Right? So when I have discrete differences, they are discrete derivatives plus dot dot dot. What is this dot dot dot? What would you write here? The first correction to this. So this, let me emphasize again, this is just 2 derivatives, right? This is like k squared. What is missing is the analog of k4. Yeah, some kind of higher derivative terms. Do you agree? It is just that when you have 3 points, you say this point minus a half this 2, its second derivative plus, I don't know, 1/8 times fourth derivative plus dot dot dot. You make an approximation of finite difference by finite derivatives. Right? So we will have terms like plus some small coupling, let's call it A. So A is going to be something small. Times something like of the form, morally speaking, something like d mu s, d mu s. But what matters is, I just contracted the indices properly, but what I want to emphasize is 4 derivatives and 2 s's. And then there are higher terms, plus even higher more derivatives. Right? Again, notice that this is exactly the counterpart of what we are doing. If I write this, for example, as Laplacian square with s and s by integrating by parts a few times, then this is literally in Fourier k to the 4. This guy in Fourier is literally k squared. So the inverse is just k squared plus m squared plus a k to the 4. Right? So this immediately leads to a propagator 1 over k squared plus m squared plus a k to the 4. Then we throw this away because we are dealing with k very small.
Actually, I'm a little bit lost on the Lagrangian. There's no Laplacian.
Sorry?
I don't see the Laplacian in the Lagrangian. I mean, that would be the inverse of the Fourier transform of the equations of motion that come out of the Lagrangian, right?
Okay, so do you agree that if it was just these two terms, this is the propagator without the a, or not?
No, because I don't see a Laplacian in the Lagrangian.
I just said s, Laplacian s.
That is, yeah, but that's not what's written up there.
I just integrated by parts. This derivative I put it there. Laplacian is in the right? That's why there's a minus sign, because I integrated by parts.
Okay.
Right? And when you take derivative, each derivative brings ik with this minus sign, which is plus k squared. Good now? Okay. So this is what we know will happen. So this is indeed, we are going in the right direction. But I don't want to do it by computing, I want to do it just by thinking. So I want to say the following. Suppose I have some dimensionless physical quantity that's a function of some distance r, right? It could be correlation function of spins, it could be some, whatever, any physical quantity that depends on some distance r, that we say that it is something computed with a equal to 0 plus a times something plus dot dot dot. Right, so I just treat a as a small parameter and that's what I have. Right? Good. And this is dimensionless, which means it's physical, right? We already, if it's not dimensionless, whatever, put here the dimension and then a bracket, and then it's this plus this, and the dimension can always be factored out, right? So physical quantities are dimensionless. Okay. Now let's do some dimensional analysis. Let's see what are these units. So derivative as dimension minus 1. So here I'm doing dimensions of length, right? Which is equal to minus dimensions of mass, right? So in mass dimension we'll put plus 1. Do you prefer if I do mass dimension or length dimension is good? Derivative is 1 it's ddx, so it's minus 1.
I prefer mass.
You prefer mass dimension? Ronaldo, do you prefer Rolando? Rolando. Do you prefer mass or dimension?
I've seen with mass, but I think that is the minus.
Yeah. So in these units, R, right, as D, right, because it's units of length. Otherwise it would be minus d. So I'm doing length dimension, right? If you are not used, it makes it at least a little bit entertaining. I'm also not used. It's the first time I'm using it. I don't think everyone ever uses dimensions of length, but that's what makes it more interesting. We are doing something original for the first time. So, and so this is dimension d. Each derivative is dimension minus 1. So what's the dimension of S to make these dimensions? So dimension of S is? Again? D plus 2? So.
Oh no, d plus 1. No, the square.
So what? What is that?
2 minus d, 2 minus
So in total,
d minus is
this dimension plus this with factors of 2 must be equal to 0, right? So what's the dimension of S? 2 minus d divided by 2. Such that 2 s's plus 2 derivatives cancels this dimension. Right? So that works. Okay, m has the same units as 1 over length, so the second term is okay. But importantly, this means that A, what's the dimension of A? It's actually super easy because you know that if you take two derivatives, it will be dimensionless, so it's just the two derivatives that A needs to cancel. Right? So compared to the first term, it has 2 extra derivatives. Right? So without the 2 derivatives, everything would be dimensionless. Because of 2 derivatives, A needs to have dimension 2. So dimension of A is 2. So A has 2 units of length. Right? Which means, important now here is the punchline. If A has dimensions of length, it means that this quantity to be dimensionless needs to be divided by r squared. If I want the dimensions to work out. And so, it goes to 0 at large distances.
But you could use any dimensional quantity when you put there. So correlation length, not necessarily the distance, right?
No, it must be because how to say it? Yeah, because okay, so let me think. How do I argue that you cannot? So the answer is you cannot. So let's recap. So what's the logic? The logic is okay, this is important. Give me a second. So yeah, let me remember what the argument is. This is correct, but I have to remember the argument. So help me out figuring out the argument. So we figure out that to make things dimensionless, I need to divide by r squared. So that's the effect that this term has. So we know it explicitly from computation that that's also true. But how do I argue like this that I cannot put just a times m squared? And that is because
I think you can, and you have both of them, because the most general dimensional quantity you have something that can put the mass, something that you put the error, but you still, yeah, doesn't
No,
matter.
that's not good. That's wrong.
I'm sorry, but are we trying to argue that every dimensionless physical quantity, which is a function of R, only depends on when A equals 0?
Yes.
I mean, I'm sure that that there must be some kind of contrived example
No.
in which that doesn't happen.
No, that's not right. No, at large distances. At large distances, this term is always irrelevant. So that's universality. That's the statement that at large distance, this term doesn't contribute. So, yeah, the precise argument is like this. So I have A. Yeah, I'm forgetting something basic, very basic about the basic philosophy of effective field theory, which is obvious, but just. So the question is why can't we use the mass, right?
Yes. Or any other.
No, but there's no other. There's no other.
Yeah.
So if maybe we can argue that dimensionless, that physical quantities in general have to come out as expectation values of a partition function gotten by exponentiating that, and if we treat A as a perturbation in that exponential, then the mass is still up, and the mass wouldn't appear in any of the other terms that are after the dot dot dots.
No, but.
It will be something like the mass is in the dot dot dot, but in RN you generate a dimensionless quantity, and then you have to still compensate the dimension of A with R. But because this is something that at least I use in effective field theory, that if you know some dimension quantity and you know the dimension of some object, you start putting this quantity until you have something that is the right dimension. So this is why how you estimate like proton decays using the mass of proton and the time of the proton to decay. But I don't know how to argue that it's not possible here. writing effective couplings, you put dimensionless quantities divided by the cutoff.
Yes. No, that you do here in the action, not that.
Yeah, that's right.
Okay, I have to think a little bit. So, if this A has natural units of 2 millimeters, the idea is that when I have a 2 meters is much larger than 2 millimeters, and therefore the effect of this term is going to be irrelevant. We could say that we could study the R dependence of the quantity, right? So even if there is a term which is AM squared, it's not R dependent, so I don't care. But whenever I study does it affect at large distances, it will always decay with the distance. But okay, for next time I will figure out. I will come back with a more clean description. I was just, yeah, I have to clean this up a little bit. Okay, but there exists a version of this argument which is clean, and the conclusion, even though this is not super clean, let me summarize what the conclusion will be more general. If I call this an operator, OI, then this operator OI, the full dimension of this guy, OI, in this case, is minus D minus 2. Right? This OI, because without the two derivative it was minus D, that cancelled the DDR, and now it's minus D minus 2. And this dimension is smaller than minus D. And whenever an operator has dimension smaller than minus D, this is what's called an irrelevant operator. And these operators are irrelevant, which means that they don't affect at large distances.
When you say large distances, is the same as saying low energy?
Yes, that's what we want to learn. Okay, so let's consider now then, based on this first exploration, let's consider adding a term to the Gaussian model, which is not this, but let's actually want to do it. So these terms are irrelevant, so I don't care about them. And I will add here another term, which would be lambda s to the 4. Now, this term here would have dimension equal to the dimension of s to the 4. Right? Is equal to 4 times that, so it's equal to 4 minus 2d, which is equal to minus d if d equals to 4. So in d equals to 4, it's not relevant or irrelevant, it's in between, it's what's called marginal. So then it's marginal. So when operators are irrelevant, they don't matter at large distances. When they are relevant, they matter at large distances. And when they are marginal, we don't know a priori, we have to compute a little bit harder to know whether they matter or not.
We saw that putting these terms in the Lagrangian or in the Gaussian model, we changed the effective mass, right?
Right.
But this effective mass could be changed to 0, and this would change the large distance.
Then yes, yeah, and that it requires some fine tuning, and that's a critical point.
But all these terms, we will have the information about this critical point.
Right, they are all here, right? All this information is in the mass. I can set the mass to 0 there.
The continual limit.
Yeah. Okay, so now I want to add this extra term to my action. So we think that the Lagrangian, I can also do it in the discrete. It's this Lagrangian where this is the usual u plus t stuff. Delta. Right? But then we add plus some interaction Lagrangian, where in the discrete language this would be sum over positions r s r. Well, the action would be the integral of that Lagrangian, would be this. Right? So now let's study, to linear approximation in lambda, what would this affect a correlation function of two spins? So a correlation function of two spins is what? It's going to be when I compute the expectation value of lambda, right? I have an expectation value which is a summation over spins divided by the partition function. So let me multiply by the partition function with lambda, divide by the partition function at lambda equals 0. Then we'll take care of this factor, but this just simplifies my life a little bit so that I can write the following equal sign. This is equal to 1 plus lambda, not 1, sorry, it's equal to S0 SR with lambda equal to 0, right? Because I divide and multiply, now it has the right C0 to be this quantity, plus lambda sum over R prime expectation value of S0 SR prime to the 4, which I write like this, at lambda equals 0 plus dot dot dot. So far so good? Now how do I compute these expectation values at 0 lambda? How do I compute this expectation value? What is this expectation value? At lambda equals 0? It's the propagator. Right? So this we did it. How did we compute it? We just do a one-week contraction, and this just gives me the propagator. Right? So that's just one week contraction. How do we compute this expectation value at lambda equals 0?
About the weak contractions.
Exactly. So now we have to do weak contractions. How many possibilities there are? How many? 48 you said? How did you count 48?
There is 6 S's, so I did 6 double factorial.
6 times what?
6 double factorial. Oh no, it's 5 double factorial.
Exactly.
So 5 times 6 is 15.
15. Let's see how those 15 are separate into 12 plus 3. There is one possibility where these two guys couple, and then these two guys couple, and these two guys couple. Doesn't matter which ones because they're all equivalent, right? That's one possibility. And this possibility we would call the disconnected possibility because they couple these two guys and then the interaction couples by itself. So let's draw in a picture what this would be. If I draw this picture, I say this is just 0 coupling to R. Then this picture is 0 couples to R, the same thing. And then there is R prime here, and R prime couples to R prime couples to R prime. Right? So it's just a disconnected contribution, this guy and this guy. Okay? Do you agree? This is R prime. This comes with what factor? How many terms are there like this? So this couples to this, and then how many options are here? This guy can couple to any of the other 3. So 3. Right? Once this guy couples, the other one is fixed. So this comes with a factor of 3. Then there is another possibility, which is that one of the external spins couples to an R, and the other couples to another R. Doesn't matter which one, I couple to this one just for fun. And then the remaining 2 R's couple. Right? And this is another possibility that's called the connected diagram. So this is disconnected. The one that I'm drawing now is connected. What would be the picture now? Well, now 0. The first one couples one of the interaction spins. And then the interaction spin couples to the external one, but they make a loop. And now we have this 0, R, and R prime. And you see that this describes an interaction. Notice that this extra term we could also think of them in the language of paths like the last time. If we bring down this term also, not only we have sticks, but we have this possibility that the wall can go and sometimes can split into 3 walls. Because we have these quartic vertices now. So the rules of the game are not just paths, it's not just random path here, but then it has the possibility of splitting. So we can think that it was a propagator from here to here, it was a random walk. Then it got here, and because of this extra term, now there's a probability lambda of exploding into 3. And then each one goes around this random walk and so on. So we could describe this as literally saying that I have a particle, goes following no paths, then it splits into 3, 2 of them go and do a random walk and then they delay, and the other one goes and goes all the way there. Right? And this is like first quantization picture, where I have summation over trajectories of particles, that's just a random walk we saw before. So that's how I would describe this with random walks. Random walk from here to here, random walk from here to here, and random walk from here to here.
When we talked about Gaussian integration, we did very general Gaussian integrals, and the key point was that we always got vacuum diagrams. Now, why do we get like this external things? What changed?
We did not always get vacuum diagrams. Well, in some examples that we did, maybe we did, but there's nothing special about the vacuum diagram. So when the propagator is an example, the propagator is this, right? And it's not a vacuum diagram. Now, why would it be vacuum diagrams? There was nothing conceptual about vacuum diagrams that was needed.
I don't remember. Yeah, maybe the line of the propagator, but then everything that we, I mean, if I remember correctly, every other diagram that we built was always closed. I don't know why. Well, it was always closed because the key point that we wanted to convey with the diagrams, I think, was that the diagrams were a tool for us to connect things.
Right. We were not worried about external things and separating between external and internal. We were just doing vacuum diagrams to illustrate the point, but nothing changes, right? It's all about just quick contract. Okay, if we did not see vacuum, if we only saw vacuum diagram, it's fine, but here is one which is not vacuum. Okay, so we get this diagram, and this comes with what combinatorial factor? So S0 can couple with any of the other ones, so 4 options. This guy can couple to any of the remaining 3, so 3 options. And once these two guys couple, the remaining pair is determined, so this factor comes with a 12. 4 times 3. Okay, and 12 plus 3 is 15. So it's okay, we do not miss any diagram. Right? But now, you see that we have to take into account this factor here, z lambda and z0. So what is this? This is 1 plus, right? Because when I expand in lambda, the first term gives 1 plus the vacuum diagram now that you're saying. Right? When I bring down the vertex, 1 plus this vacuum diagram. Right? And this vacuum diagram comes with what coefficient? It's 3 double factorial, which is 3. Huh? So you see that this factor here cancels the disconnected part. Do you agree? So this factor here cancels this factor here. Is it okay for everyone? If I divide by this factor, expanding lambda, let's put the lambda here. That term gets cancelled, so I get only the connected term, which is what we expect. And so we conclude that this quantity, that the expectation value of S0 SR is equal to this propagator plus 12 lambda times this graph plus lambda squared. Okay. So let's write what this graph is. Let's write this contribution here very explicitly, this weak contraction. So each is a propagator. There is a sum over R. So let's write it carefully. So this diagram gives sum over R prime, product of 3 propagators. So let's write each propagator very explicitly. Each propagator is integral d k1 over 2 pi to the d, where this is the k1 so that I will use to write this propagator. Then I will use k2 to write this propagator, and I will use k3 to write this propagator. So we'll have 3 integrals, dk1, let me just use a notation like this. This integral over k2, this integral over k3, right? Or by this I mean all this stuff, so that I don't have so much work. Then I get a bunch of exponentials, e to the I, k1 times this propagator that goes from 0 to r prime. So the distance here is r prime. You agree? What multiplies k2? So in the exponent, k1 comes with r prime and k2. 0, because it goes from the point itself, so there's no k2. And k3? Sorry? Yeah, minus r prime because I wrote a mistake here, it was r. Right? So 0 to r prime to r. R minus r prime. And what should I write downstairs? propagator factors. So let me write 1, 2, 3. Right. Where what is omega? Omega would be u plus 2t sum over mu of cosine of k mu. Right? So far so good? And this is approximately equal, if you want, some constant times m squared plus k squared. But we can use the exact result. So is everyone happy with this expression here? Okay. So what should I do now? Ivan, you seem lost. Are you lost? Or?
Yeah, a little bit. Did we evaluate the diagram? What was the logic?
So what is this expression equal? This weak contraction. It's product of 4 propagators. So this graph is equal propagator from 0 to r prime times propagator from r prime to r prime times propagator from r prime to r. Do you agree?
Okay, I got it.
So then we just wrote each propagator as an integral over k. Now what's the next step there to simplify that expression? What can I do?
Use the sum of r to remove a delta.
Right? So the sum over r does what? So first of all, there is a factor that sorry, just a second. So sum over r prime. Sum over r prime is good. Then okay, there are some volume factors that I'm not being careful about, but okay.
Why do you think that there are some factors?
Because this propagator will be no, actually maybe not, sorry, maybe not.
I think that's good. I mean, there are extra factors once we do the expansion of m squared plus k squared.
Okay. I'm not sure if there are some volume factors missing or not actually, so 1 second. So
It depends what
the
is
propagator was 1 over volume and then we replaced by integral, so it looks okay. This is okay, sum over r prime looks okay. Yeah, it's probably everything is okay. Okay, so when I integrate over r prime, what happens? When I sum over r prime?
create a delta of ku delta.
Exactly. So the integration over r prime, the summation over r prime sets k1 equal to k3.
And you integrate
Right?
k1
It gives a delta function that sets k1 equal to k3, which means that I can just, this summation also kills the integral, so all this goes away, right? K1 and K3, K1 and K3 disappear, so this term disappears, this term disappears. Okay?
Why did the sum kill the integral?
The sum gave delta function,
Gave
and
delta function or direct delta?
gave delta function of a K1 being equal to K3,
Oh, okay.
and then that integration is it clear or not? And yeah, it's actually an identity that I did not use yet, but the identity I'm using here is the sum of r prime over an infinite lattice. I don't know if you, I mean, actually I don't think we use this identity, the one we are using now. Because we normally do things either totally discrete or in the large lattice approximation. So here we are using that sum over r prime e to the I q dot r prime is equal to what?
delta of ku.
If I sum over R prime is an infinite lattice, I sum over all positions, and you are saying it's delta. Okay? That's not true. Any other proposals? So let me write an equation which is true. Integral dr e to the ikr is equal to delta. That's true?
With the 2 pi.
Yeah, some 2 pi's, yeah. 2 pi's of course. But this one, I sum over all positions.
Yes, if you discretize the parameter, you get the same thing but a volume factor.
Okay, the identity is the following. So this one over R. When k is 0, indeed it gives infinity. So it looks like it's good. But these k's are in the are between minus 2 pi and 2 pi. And R is discrete, so I cannot distinguish k from k plus 2 pi. So it gives me plus 2 pi e mu and mu, and it gives me a sum over n mu from minus infinity to infinity. So it gives a train of delta functions
You cannot distinguish k
from k plus 2 pi. Because R takes value 1, 2, 3. So if I add k 2 pi, I cannot distinguish. So this right hand side must be periodic in k. So it's not a delta function, it's a lattice of delta functions. If I add in 2 dimensions, it's like this. It's a lattice of delta functions. Okay? But we integrate in a Brillouin zone, and the Brillouin zone is like this. So effectively, we only see one delta function. We don't care about going outside, and therefore what we did is correct. Okay? But in general, it would give a train of delta function like this. Okay? So that everything is good. So it's important to notice that we got an integral of k2 times an omega of k2, and then an integral over k3 and an omega over k3 here, and another one here. Because I remind you that these k's are identified, so I should go and change this k1 to k3 after integrating. Right, so I have k3, k3, and k2 here. And so, the effect of adding this perturbation was to give me an expectation value which is equal to this graph. And you see that because there is a single integral over k3, what's inside the integral over k3 is the Fourier transform of the result by definition. Right? Because there's integral over k3, e to the k3 times r, whatever multiplies is the Fourier transform by definition. Do you agree? So what's the Fourier transform? So let's do it in Fourier. In Fourier, right? Our propagator s k s minus k was equal to 3 level, which was 1 over omega of k, that was just a propagator, right? Plus, and now there in Fourier we see it's 1 over omega of k, that's this part here. Then there is this loop, which is a number, and that number is integral ddq over omega to the q. That's a number that describes this loop here. And then another propagator, 1 over omega of k, that describes this propagator. Right? And so the picture is quite clear that I have some momentum that's conserved, And if it splits here, if this has momentum q, this must have momentum q because momentum k must be conserved. So there's k, and there's q, and we integrate over q the momentum there in that loop. So this, we would call this loop. Okay? And this came with a lambda, right?
I didn't understand the Fourier.
So this is just a Fourier transform of the propagator.
Okay.
What is the Fourier transform? How do you recognize a Fourier transform?
Say what is multiplying the.
Right, so the Fourier transform, so this, right, it's a function of r. Here I multiply by k3, I integrate over k3. So whatever I take out as exponential, the rest is the Fourier transform. Okay, so it's a function of k3, k3 is k, so there is k3 here, those are the k, and q2, I will label q small q, these are letters on myself. So this was k3, this was k2.
Okay, I see the second term. Why is the first term?
By second, you mean this? You mean this? No, this was just the trivial propagator. Right? So our propagator was this plus this, right? This is just a propagator. It is just S0, was just S0, SI. The Fourier transform. This is, by definition, the Fourier transform of this, right? Yes or not? Right? This guy is the Fourier transform of this. Do you agree? That's how we solved it. Okay. So that's at lambda order. So at lambda order, we start seeing a picture where particles start interacting, and now they don't only random walk, but they do something funny in the middle. And now what would happen at order lambda squared? Based on this picture. Well, at order lambda squared, you bring down two vertices. Okay? So if you bring down two vertices, complicated things could we could get complicated things that we are not going to even try to compute or discuss. But let's write the pictures for them. So what could I draw where I have one external spin, then I have one vertex, then I have another vertex, then I have one external spin? What kind of connected graphs, new connected graphs could I draw? So these are the ingredients. So let me give you an example. A new graph that I could draw is this. Right? A particle comes, splits in three, join again, and goes. Yeah, this is more interesting. It's more complicated than the one we studied. Because this is just a number. So from the point of view of k, the dependence on this term is just the previous propagator squared times a number. And that was because the loop doesn't know about this momentum, right? The loop must conserve momentum, so whatever goes here must come here. Whereas here, if momentum k is here, and if momentum k goes here, here I have a propagator 1 over omega of some momentum q. Here, let's say some momentum L, so 1 over omega with some momentum L. Then here, the momentum must be K minus L minus Q. So 1 over omega K minus L minus Q. And the result of this integral, of this picture here in Fourier, will be the integral ddq ddl, this is this inside part, times these two propagators here, this one and this one. So again, 1 over omega from the left, all this, and 1 over omega of k from the left. Okay? So this is the result that you would get if you would go through the painful algebra that we did. You would have double sum over R and R prime. Those sums allow you to, what do those sums do? They put momentum conservation, they impose that all K's that meet here are 0, that's the same thing as before. They do the same thing here. Once they impose momentum conservation, the picture is clear. Okay? And therefore we get this, where now this is not just a number. Now it really, this middle part here would really depend on K. It's a function of K. And it's a function we would have to compute. Right? All this that I'm drawing here, this is what are called Feynman diagrams. All this thing here are what's called Feynman diagrams. And that's the beginning of a technology, understanding how to compute Feynman diagrams, to write down the perturbative expansion. Diagram of time with lambda square. Okay. And that's not the goal of this course, to go into Feynman diagrams, but I wanted to point out that we see here very naturally how they would appear in these statistical mechanical models. But let's write another graph that is a bit simpler, which is this one, where I will just have two bubbles. Right? So this one is not more complicated than the one we had before, right? This one is just the bubble put another time, twice. So what is this one in Fourier?
I would have two loops.
Exactly, so tell me, what should I write here?
Propagator.
One over omega of k, good, then loop, propagator, loop, propagator. Right? Plus dot dot dot. The number of graphs starts growing very fast. There are even more graphs that I could draw at this order. These are just two of them. The number of graphs grows very fast. This leads to these expansions being asymptotic, so we need to be careful. But let's see what happens if I resum some of them. Let's try to resum this graph of this type. This one, and this one. This is 0 loops, 1 loop, 2 loops, 3 loops, 4 loops. Let's resum this chain to get an idea of what will happen. Okay. So what happens when I do this? What do I get when I resum this chain?
Geometric sum.
It's a geometric sum, right? So these are Feynman diagrams. And the sum over loops, let's see, what would this be? I would start with 0 loops. Okay, let's put n number of loops from 0 to infinity. They all come with the first propagator, 1 over omega of k, and then they come with loop times 1 over omega to the end. Right? But this is just geometric series, so this gives 1 over omega of k plus loop. Yeah? Is this clear? Now 1 over omega of k plus loop is what? Is 1 over u plus 2t sum cosine a mu plus the loop, which is lambda times a number, and that number is the integral the dimensional q over u plus 2t cosine q mu. Right? So this is just a number, so it's a constant, c. So So finally, what's the effect at large distances?
Change you.
Yeah, the net effect is just changing u. In other words, the net effect is again some mass renormalization. Right, so all this does is change the mass. It shifts the propagator from k squared plus m squared to k squared plus m prime squared. And I can interpret this as a change in the renormalization of my mass. So far so good? Now notice that everything is finite here. Indeed, that's why we wrote it in this lattice language. But suppose we had taken the field theory limit before. Right? So in the continuum, however, this would be a bit dangerous. Right? So in the continuum, if we start in the continuum, what should we do at large distances? You see? At large distances, this k is conjugate to e to the ikr, I can expand at small k. Right? So in the continuum, when the distances are much bigger than 1, I should write 1 over n squared plus k squared. That's obvious. Right? But what about q? Should I expand in q? Well, q is just a number. Right? A priori I shouldn't. I just compute this and that's it. Right? But if I started by taking the continuum limit before, then what I would get, so this is okay. This is perfectly okay, I should do this. But this one is dangerous. Because I'm going to take the continuum limit before and then write that this is lambda times an integral d dq over q squared plus m squared. Okay. And now, this integral here is divergent. Right? Because indeed, at large q, it gives dq, q to the d minus 3. Right? So it's divergent for d bigger than 2. Yes?
In the lattice, the integral has a bound domain, right?
Exactly. Here, the integral q is smaller than pi. Right? Or pi over a if I had a lattice spacing, so there was a natural cutoff. As soon as I say that I expand at small q, because only small q matters, and then I extend to all the integration domain, now suddenly I find infinities. To regulate these infinities, we would say that the absolute value of q needs to be smaller than some cutoff. After all, that's what the lattice was telling us from the beginning. Right? And this cutoff is what? This divergence that we need. We need counter terms, we need to regularize. This is nothing but our lattice ignorance. It's just okay, you can take the continuum limit, but then you lost the information that there was a lattice there and how things are regulated. Right? So what you can do is put counter terms that codify that ignorance, that says that this should somehow be regulated because there is a lattice. So I put some kind of regulator and then get rid of the regulator by expressing everything in terms of physical quantities. Any question here? Any question about random walks or Gaussian model? About standard random walks or standard Gaussian model? We could ask, for example, what's the field theory description of the models that Mateus described, which were not the usual random walks, but these funny ones. I don't know the answer. Okay, that's a question. What other questions could we ask about random walks and Gaussian
I
walks?
have one question, I don't know where in the literature has this, but the question of going to infinite correlation length or using different couplings in the lattice. So, you know, somewhere that they did that.
Parisi probably it's done. More questions? So you see, Gaussian model is just a Gaussian, so it can be done exactly. Perturbations around the Gaussian model is just weak theorem. You just bring down and it's again Gaussian integrations. Because it's just weak theorem, it has this graph picture. And because each segment of the graph, which is a propagator, we gave it a meaning in terms of random walks, we can give a meaning to any graph by saying that this is really quantum mechanical particles that go, split into three, randomly move around, meet again, and so on. Because we already gave such meaning to a single propagator. And that's the basic picture of Feynman, that these Feynman graphs encode the sum of stories of particles. And we see it very explicitly here. Okay. So it's 12:37. We have 20 minutes, but I will not use the 20 minutes. I'll summarize a little bit what we are planning for next. So let's summarize a little bit what we have seen. So we have seen random walks, where I have a random particle around a random walk that can do anything like this. It can also go back. It had bias, no bias, we saw this. And we saw the Gaussian model. Which was an integral of a product we sum over all spins. At each spin, the spin takes value from minus to plus infinity. Exponential of minus summation over r of u over 2 SR squared plus t summation over the edges of S, I, S, J. I changed the notation, I and J now is notation of the edges. Right. And I remind you that we saw that this partition function could be written in the following form. We could say that this is a sum over configurations Nij, where at each side I can have 0 sticks, 1 stick, up to infinitely many sticks. Right? This was from expanding the exponential. Then there was a constant outside. Right? Then there was a t over u to the total number of sticks, sum over Nij. Right? And for each stick configuration here, there was a weight that was a product over all sides, and then we had Ni minus 1 double factorial. And we have product over edges 1 over nij factorial, where this ni was the number, the summation over j of nij, the number of sticks that leave side I. Right? And we saw that this guy needs to be even. That is, it needs to be 0, 2, 4, and so on. Minus 1 double factorial is 1 in this language. And this was describing this configuration that I need to put an even number of sticks, so I can draw these easy configurations. Then we also discussed a bit these more complicated ones, or even also ones which self-intersect. And when we matched these to paths, we saw that this was a summation over paths, precisely because of those factorials, because this term, for example, I could interpret this intersection, I could resolve it like this, or like this, right? And these three ways of resolving was the 3, which is the 3 double factorial that would come if I put ni equals 4. Right? This was from ni equals to 4. Right? And the combinatorics were such that this was really a sum of closed loops. And this was the result when you have I spins at position I, you integrate and you get this. So this is what we would call some m ni. It's the notation Parisi uses. Is the weight, this m ni, that's the important thing, came, very importantly, from integrating s to the ni e to the minus s squared over 2. That's the definition of that m ni. Right? And that's this double factorial there. Okay? So, now imagine it was not s squared but s to the 4. This term, I would like to change it to s to the 4. That term I keep, but this I change to s to the 4. Okay? What changes in that expression? Yeah. This is the same. This is from expanding exponential. Everything would be the same, but here I will change this 2 to a 4. And now this is a complicated weight. And because this weight is complicated, I probably cannot disentangle it and think of this as just paths. Right? But this representation will also be true. I just replace this mn. Right? The fact that mn is given by this with a 2 here is because I start with a model where I integrate over Gaussians with weights 2 there. Right? Now it's Gaussian, so we could do the integral. It's not Gaussian, sometimes we can, sometimes we cannot. But it's not just exclusivity of Gaussians. Okay? So next time, we'll start with this model, but we'll study a little bit, we'll take this opportunity for studying a bit the Ising model, which is a very important model. And the Ising model, so this is Z. In the Ising model, Z, I don't integrate over spins, I sum where each spin is plus minus 1. Right? Then that's what replaces the Gaussian. And then I have e to the minus beta j, sum over the edges, as I as j. Or you can use the same notation, we can call this e to the t as I as j. Okay? And that's going to be our starting point. And we will ask here, we will do two things that I think are interesting. One is we find sum over loops into dimensions. Akin to this, now we follow the same strategy but with this. Right? We expand down, everything looks the same, but you see, because of summation instead of integration, what will replace that amending that integral of the Gaussian is now a sum over two values. Okay? So can you tell me what do you think this mn's will be when I sum instead of integrating? Right? So it's summation over two values rather than integration with the Gaussian. So what will change? It will be exactly, it will be 2 if n is even and 0 if it's odd. So instead of that double factorial, now it's a constant. That's it. Okay? So we'll do it more slowly, but that's it. You already did it by head. Indeed, this was if it's even, and this factor is 0 if odd. And now, as you're pointing out, it's 2 if even and 0 if odd. And now we have to think again. What about this combinatorics? I no longer have this double factorial. So we'll have to think a little bit what changes in this picture. And then this will lead to a solution of the model. And that's the solution that Onsager found. That's an important milestone in physics, the solution of the 2D Ising model, so we'll solve it. Now another very natural thing would be to study this model in one dimension. Because in one dimension it's actually exactly solvable as well, it's much simpler to solve exactly. It's very nicely described in this book that I recommended, in the normalization book. It's in the RG book, for example. Did everyone study this one-dimensionalizing model? Yes? So do you know its solution of the 1D? You know the solution of one-dimensionalizing model?
I don't remember it clearly, but I remember that it's easy to
Okay. So I would suggest that this would be the topic of a presentation. And then I will explain the 2D one. But 1D, I think someone could study this and give it as a presentation, if you guys agree. Okay? So that's, I think it's perfectly explained in the book. There is a book that I recommend by Creswick, and it's section 5.0, 5.1, and 5.2. That's the one-dimensionalizing model. Extremely well explained, and you can complement it with any other reference. So someone could give a lecture about the 1D Ising model if you agree. So one of the two of you. If you never saw it before, I think it's more interesting because if you have already seen it, I would suggest. If one of you did not see it before, I would suggest that whoever did not see it before that would present it.
The 1D model you solved by transfer of numbers.
For example, by transfer matrix. By presentation, I mean solving it exactly, for example, by transfer matrix, and discussing also normalization for this model. How do you interpret those results from normalization? I think the book is very good. It's basically reading the book and presenting what is in the book. So, and if you have more comments, because there are so many solutions of the 1D Ising model, we can complement. So I propose that someone gives a presentation about this. So we would have already one presentation from Vieira on matrix models. What else was scheduled? Was there something more?
Yeah, I was supposed to give the relationship between source and
self-avoiding logs and again over this model with a vector model for OM.
the spherical model.
Yeah, spherical model. Okay, so you could do that. So would you like to talk about the 1D Ising model? Okay. So Polanco?
Yeah.
Okay, so Rolando will tell us then about the 1D Ising model, and I will tell you about the exact solution. So the material should be this class-week book, the normalization. But if you have more things to say, more nice things to say about the 1D Ising model, that's totally fine. But you can solve it exactly, compute correlation functions. And I want to emphasize to the discussion of the relation to RG to be described. So I want solution plus RG. It's simple enough that everything can be done analytically in 1D, so it will be to describe this. Okay? The relation to walks, why the spherical model is related to random walks, I think we can already do it at this moment, right? We already have this technology of relating models to walks. I think we could already, so another direction, that's a generalization, is go to spherical model and relate to another type of walk, self-avoiding walks. We could do that after seeing this one. This is the second example where we relate to walks, and then this will be a third example. But it's actually a bit independent from this. In a way, this self-avoiding walks is a bit easier than this. So I think this could be already a presentation by Ivan, as you said. So we have Vieira matrix models. I think we could next have, I don't care, either of these three. So one proposal is that since you record it and I can watch it online, I can even put the video on twice the speed, which is good.
We can do it with you online at the time. I can put the Skype or any other.
But you can also, if all the four of you are present, I just don't want you to give the presentation for one person like yesterday. That was not nice. But if the four of you are present, I would suggest that you give all these presentations and record them next week. Like you have, because I'm not here next week, so you have Wednesday, Thursday, and Friday, and you feed these three presentations on those 3 days, and you give 1 hour each, and you record it. Maybe I can watch it online, maybe not. I'll be in Natal, and there are talks in the morning, exactly. So I don't think I'll join. But I will watch it afterwards and give comments and complement whatever is needed. That's one option. The other option is we do the presentations a bit later. But I think, we already wrote a matrix model like 2 weeks ago. We are going to forget what this is. I think definitely we should solve one matrix, say something about one matrix model. And then I'm traveling, so let me find out when I'm coming back, because I forgot when it is. So. Janeiro, fevereiro, março.
So do you guys think it's a good idea to just do it like next Thursday, but maybe earlier?
So I come back 17. When is 17? Is it Tuesday or Wednesday? 17 is Wednesday? Okay, so we have 3 lectures to fix. We have Wednesday, Friday, and then the next Wednesday. So I'm out all these days. So this Wednesday here, let's move to Thursday at 11. Can we? The 17th. So that one is still. Okay, so Thursday 17th, go to Thursday at 11 a.m. on the 18th. Then Friday is good, and so on. And then we have to fix these two. So these two, there will be no lecture, and we replacing a bit earlier. Otherwise, if I have to travel some other time, we'll start having many lectures missing. But yeah, but this week is empty, so.
I think it's okay with you to try to do online here using some Skype and do at least one presentation next week from Victor. That I think he'll be prepared to that. And then we can try to find a nice time to do it, depending on your schedule.
Did you start studying the relation to the self-avoiding walks?
No, I was with it. I tried to look it up. I couldn't find anything. Can you send me the references?
So one of the references that in the pages I gave was McGreevy's lectures, right?
Okay.
On McGreevy.
Not the paper.
Sorry? In the paper that I gave you.
McGreevy.
Yeah, there are the lectures on McGreevy. There he discusses the M to zero limit, and he refers to the to the book of Cardi and to the book of Brezin. So, but the reference is in McGreevy. So if you go to McGreevy, from McGreevy you find the other two references as well. So that would be it for the self-avoiding walk. It's McGreevy and the two references that he has there. And McGreevy has some lectures on generalization, which are very good, and I refer to them in my notes. And for Ising, it's the book on generalization by Keswick or Credwick. I don't know. It was generalization methods for physics. The name. Yeah, no, I don't. But it's a very good book, and that's about Ising. And the matrix model could be the book by Marco Marino, for example. It's a very good book on matrix models, and that could be the reference for Vitor. So chat with Vitor and send me an email with a proposal. So let me check one more thing. We can stop recording. Let me check.